guys, as I go live with this, I have to mute the live stream. I think I have this. All right, guys. So let me, then I'll have to share a different screen, which I can do by doing what? 1 second. Share this. All right. Are you seeing this picture?
Yes.
So what happens is, when you don't regularize, in the parameter space on the plane, the contour lines are here, the minima is here, the optimal beta is far from the origin, right? And you say that is fine. Unregularized means you take this as the solution. Regularized means you put a constrained surface, a unit circle of some norm, and then you look for this point. So this is regularized optimal point. This is the unregularized, just the sum squared error for regression, for example, point. And for different algorithms, it could be different. For example, in a deep neural network, the error surface is not so simple. It is not just a bowl shape. It could be highly non-trivial, but nonetheless, an unregularized solution would be you take the parameters wherever the minimum value of the error surface falls.
Asif, can you explain again? Like, for some reason, I'm not able to see your mouse. So, yeah, I don't get that intuition.
See, all right, let me try this. See, my mouse is not visible. Okay, do you see this point here?
Okay, yeah.
This is far, wherever it may fall, right? The error surface will achieve a minima somewhere in the parameter space.
Yes.
It may form a minima pretty far from the origin. Far from the origin means large values of the parameters. Right? So this is true not just of linear polynomial regression, etc. It's true of all modeling. Unless you regularize, your error surface may find a minima very, very far from the origin. So origin is here. You don't want that. The whole point of regularization is you want to make sure that your parameters are all small. To do that, you put a budget, you put a unit circle, a circle of certain diameter, and you say that this is my budget. I'm not willing to go out of it. Right? So it's sort of like the Lakshman Rekha around the Panchvati. You go here. Now you find the minima here. This is the regularized minima. Sorry, what's happening? This is the regularized minima. This is the unregularized minima. Did you get that?
Yeah.
That's all I was. That's all. This is it. This is the theory of regularization in simple terms that we are talking about. Huh? Let's go to the other one now. Oh, where am I? Combined quiz, right. So that's why this is explained. What is Gini? We have done through that impurity index. Now look at this curve, guys. This is concave. What will it represent? A norm of L is equal to half. Go back and see the norms that I drew. I don't know where I drew the norms. Different shapes of the norms in the notes. If you go back and look at the videos, you'll see that this is for down. On the other hand, this is the opposite of it. This is as bulged out as it possibly can be. Right?
Yeah, so Asif, for this one, my only thing was, you said Manhattan distance. So, or is it like a Minkowski distance?
Oh, Manhattan distance norm. By the way, I made a mistake. It should not be, it should be Minkowski distance norm. Guys, I apologize. Everywhere.
I wanted to actually tell you that, like, because some for other questions also, it is Manhattan distance, which is
The typo there.
kind of like different context.
Yes, no, you're right. I have to go and fix all these questions now. I apologize, guys. I was just sitting today morning and I didn't get a time to review these questions. So, all right, there we go. It should be Minkowski distance norm, L is equal to infinity. This is the diamond. Obviously, it should be, yeah, oh my goodness, every I've used
Yeah,
method.
yeah.
Yeah.
Means at one place it is correct because you said Euclidean distance L equal to 2. So there it is correct.
And here also, F
Oh,
is,
no, yeah, this is also correct. Like Manhattan's
The next
distance.
circle one.
Yeah.
Circle one is correct.
yes,
One is also correct. Yeah.
I apologize. But I surprisingly, most of you understood what I was trying to say. So most of you got it right, which is good.
And
Now,
Good.
also, as if like in a few questions, the circle is not visible. Like I couldn't see the picture, like when the figure, basically.
that is odd.
Yeah, I couldn't see that. So I skipped that question actually.
Oh,
So that might be a browser issue, like on your
Yeah.
side. Maybe you have to delete your cache or history and then write again.
Okay, okay.
so what is information gain? Of course, it's from the last time I would do. Large hyperparameter values lead to what? They'll over dampen. Large lambda means small budget. So your parameters will become too small, right? And that too,
So that is bias, right?
yeah, you end up with a lot of bias. That's true.
Yeah,
And
okay. Yeah.
There are two corrects here, right? Right?
yeah,
Okay, okay, yeah, that's
so
what I
that's
was wondering.
excessive dimensionality reduction for lasso. Then this question is just pure definition. What is the definition of it? Remember the diamond shaped. The L is equal to 1 norm is here.
Absolutely. Yeah.
Here I was saying as if A and B are same, I think.
A and no, there's a plus and there's a minus.
Okay.
Plus lambda minus
Yeah,
lambda.
sorry.
Yeah.
So lasso regularization is superior. Of course, this is the no free lunch theorem. No one
Yeah.
thing is superior to the other always. By the way, there was a I still have to fix it. It should be a plus sign, but most of you got that right. It's a review question. Here I use Minkowski correctly. Which of the following is true? These two answers are true. The Minkowski is L is equal to, the ridge is L is equal to 2 and the lasso is L is equal to 1. Random forest we won't go into. The polynomial regression without regularization, the model tends to overfit the data. And we can see how, because the parameters become very large in absolute terms. Next, for polynomial regression without regularization, the error surface achieves its absolute minimum unacceptably far from the origin. We just talked about this. Geometrically, in ridge or lasso regularization, we do a constraint optimization where we search for the minima, right, within a using. So what is the constraint that you have to find the minimum error within a unit circle, right? So you'll typically found it at the edge of the unit circle for linear regression, but for others it may be different. That's how it is.
Okay.
Ridge, literally the definition of ridge, you use a circle definition. You know, x1
Correct.
square plus x2 square is equal to r squared.
That's correct.
Bagging, we won't go into bagging.
Sir, 27. Can you check the 27, sir?
27. In a decision tree, one can get a measure of the relative feature importance for each of the features in predictor. A decision tree gives you feature.
This is false, right? Because we said for random forest, we get the more feature importance and not for decision tree.
No, you get for both. See, the one that gives you the biggest information gain is your most important feature. If you split along whichever feature,
Right, correct.
so you take the average gain, the information gain from each of the features, you can get your answer.
Oh, relative feature. Yeah, okay.
Yes. So, okay, now this is a regularization question. Elastic net is the use of both L1 and L2. Remember, this is what we've ended with. It tries to take the virtues of both. The demerit is now you have two parameters, lambda 1, lambda 2. So you have to do more hyperparameter search. But if you have the computing power, go with elastic net. The L is equal to 1 Manhattan distance constraint leads to dimensionality reduction. Why? Because you'll puncture the error surface along one of the axes, the pointy diamond. The L2 regularization leads to dimensionality reduction. Actually, it doesn't. Why? Because all it does is it will make certain values small, but never zero. You don't tend to touch the error surface along the axis, Rarely. Lasso has the additional benefit of dimensionality reduction. Remember, that was the point, right? If you puncture along the axis, you get dimensionality reduction. And this is literally the definition of Manhattan distance. Manhattan distance is the taxi driver's distance, the shortest taxi driver's distance in Manhattan between two intersections.
So Asif, like in future, the definition may change, right? Because in Dubai, they're doing the flying taxi.
Ah, that's right.
Yeah.
And we can't talk of the taxi.
They're testing the flying taxi, yeah.
Wow, very nice. Dubai has always been very progressive. I don't know how they can afford to be so. I guess it's the oil dollars, right?
But
Oil.
this is Manhattan.
Can always say Manhattan, right?
Yeah, yeah, that is true. Yeah, Manhattan. Yeah.
Distance is another of Euclidean distances. No, the other way around. Euclidean distance is one of the Minkowski distances. Regularization is a powerful tool that we should use aggressively in model building and set the hyperparameter lambda to high. So this thing, I deliberately worded it in such a way that it would be false. Regularization is a good idea. You should always try it, but it leaves you a problem. You have to tune the hyperparameter, and high values of hyperparameter are not necessarily good.
Yeah.
The next regularization is the process intended for the suppression of bias errors in predictive model. No, it is to reduce variance errors, overfitting. And that is it. That was the quiz today, guys.
Very good questions. Very good refresher, Asif. Thanks.
Yeah, you're welcome, guys. So today, just as a reminder, today we are not doing the lab. The attendance becomes too low on the weekend. So it's an important lab I want to do when all of you are present. So we'll do it on the weekday. We'll do it on Tuesday.
So Asif, I have a question for descent trees.
Yes.
So in the descent tree, we say that it can do linear regression also.
Yeah.
So how it will create the rules? Like for every change in X, it will create a estimate value of Y, something like that? Or like X between 1 and 2, Y is 3.
Yes. See, given an input vector, it will predict a Y. How will it do that? That point will belong to some subregion of the decision tree, right? Decision tree breaks the whole feature space into subregions, isn't it? So your point will fall into one of the rectangular regions. All you have to do is take the average Y value in that rectangular region. That is your prediction for that point. Are we getting that? Let me draw it out for you. This may be worth looking into. But did I get your question correctly there?
Yeah, we can take like a 2 feature example and Z-axis as like a...
No, you don't need a Z-axis for, okay, for regression, yeah, we can take the Z-axis for regression. So here's the thing. Let me just draw it out in 2 dimensions. Suppose you have so I'll just randomly split this regions. Yeah. I don't know, something like this. Take this to be a decision tree. Let us take an arbitrary point. Consider an arbitrary point, let's say X, right? X happens to fall in this region. So what will you do? This region contains a lot of points. Let us say that it contains points like, let's add some points. Associated with each of these points is a Y hat or a Y, isn't it? Because this is training data, isn't it? So all of these points are Xi, Yi in the region where Xi, Yi belong to this region R.
Subspace, yeah.
Yeah, so this region belong to the region.
So all the Yi will be same, one value for one region?
No, that's the point. So if you want to make a prediction, your Y hat, right, of this point X is equal to just the average 1 over N of the Yi belonging to the region K. That's it. You just take the average of the Ys in that region. So yes, all the predictions in the region will be the same. The y hats will be the same. Not the y, but the y hats will all be the same. Okay. So this will, each region, let me just say, each region will have the same y hat prediction. That's it. That's how regression works. Yeah. And the way it works is that because of locality there, you expect that the y's to not be very different. Yeah. So the average y to be fairly representative.
Okay, yeah.
That's all right, guys. So with that, if there are no more questions, I'll let you guys go. Tomorrow we have the seminar. Remember, we are getting that IIT professor. He's a very interesting person. He'll be giving a talk. I hope the talk will also be interesting. He's a very simple person, unassuming, and it will be fun, I believe, to listen to him. If you have time, do please come to the talk. In the afternoon, time permitting, we'll also do the project reviews. People who need help with the projects, welcome. We'll talk a little bit about it. Let's see if I can help you. Monday, we will do boosting. This is the last topic. And Tuesday, we'll do the lab. Wednesday, we'll do the lab. Okay. And then we'll follow it up Saturday with the quiz. So we are coming towards the end of the workshop, guys. Are you guys having fun with the workshop so far? Is it proving useful?
Yes. Yes, sir.
Yes. Yes, sir.
Learning.
So get ready for the continuation. The next thing would be the math, and then after that, the boot camp. The deep learning bootcamp I've designed in such a way that it is a very logical continuation of where we end here. I don't know how many of you have registered. I have to go and see, but it will help you guys. Deep learning is the hottest topic these days.
When will the math class start, Asif?
I want to start right away. As soon as, when is your class ending? I don't want to keep a gap. So we are ending on, let's say, 22nd, if I include the Saturday, 25th. It's a pretty good idea to start. Let's leave 27th aside, maybe 27th or 3rd.
Maybe third.
Third, yeah, give a week's gap and then start on that.
Have we started what to say, the math class registration?
No, unfortunately, I still have to create the registration form, guys. Bear with me. I'll maybe do it tonight and announce it. So, and it will be the same fee structure, but the hours, I may squeeze the hours, guys. I may make it. Actually, I don't know. Maybe the boot camp I should push by 2 weeks and keep this to 6 weeks again. Or are you guys open to coming here, like formally 3 days a week for the math? We can move faster, but the risk is it may be overwhelming.
So I think 2 days a week is
Intense.
reasonable.
Yes, intense enough. Okay.
Yeah, because we need time to digest that information.
That's right. So then we'll push the boot camp by 2 weeks and do this in 6 weeks, the regular 6 weeks.
Yeah.
Asif sir, you are changing the book this time, right?
Boot camp, I may push it by a week.
No, you're changing the book for the math this time, right? Textbook.
Yeah, I'm taking the boot camp, yeah. So that the math class can be squeezed in between.
No, Asif, his question is which book? Are you going to use the same book or a different book?
No, the book is different. Yeah, the book now is, I forgot I put it in the Slack. Do you guys remember? Okay. Yeah, I put it on the Slack. It's unfortunately it's at support vectors. I'm at home, so I don't see it. Can one of you please repost the book title?
I think it's like mathematics of machine learning or something.
The mathematics of machine learning. Okay, why don't we explore it on the sort of.
It's on the Slack already. Yeah.
It is on the Slack. Huh? Is it a pinned item on Slack?
Yeah, it's not pinned, but
could you
the
repost
PDF link to the Amazon, both are there.
Okay. Let me just for fun take you to the Amazon once again. What do I do? I will go here.
Mathematics for machine learning.
Yeah, you like this book. It is simpler. It's easier than the previous one that we are used to.
Wow.
machine learning. Yeah, this book. You see this book?
Oh yeah, yeah.
This is the book. Let me post it again. So, machine learning.
Asif,
Yes.
how important is this book?
Well, all books are important.
Right.
You can get a free PDF of it.
Or
Yeah, the free PDF is available. Okay. Yeah, you can browse through it. See, here's the thing. It's a very elementary book, but the math that you need for machine learning is not deep. Unfortunately, if you don't know it, machine learning as a subject feels very intimidating. Which is the reason that once in your data science career, you should do the math of machine learning, or you should do it. Obviously, as you notice, it starts very, very simply. It talks about basic concepts. What is a vector? It really starts from there and goes from simultaneous equations that you did in maybe middle school or high school, and it develops matrices and so on and so forth. So in a way, you know, if you know your math, you will breeze through this book in no time, right? You may even feel it to be too slow. If you don't know math, fortunately, it's not intimidating. It is still just the right level that if you have forgotten your math, you can, if you remember, if you've been through high school, you'll clear this book easily. And it has a lot of colored pictures to, you know, explain the intuition about vectors, and spends a lot of time on basic things. Amazingly, that's all you need, right? Machine learning, that's all you need. And you will get a grinding in all of these things. Like, for example, what is a, like, for example, in support vector machines, separating, let's see if it takes us there. Yeah. Look at this classification, you get the concept of separating hyperplane. Well, I use the notion of a river. These people talk like this, and this is it. And it goes into the kind of math that I would like to go into with you. I haven't gone and explained the SVM. I give you the intuition, but not the math. So you will get the math also here. That's it. You do this book or you do this course, after that, you will never get intimidated by deep learning or machine learning. Any of the research papers, they'll all feel very easy. That's the purpose. All right, guys, so I need to run. My family is waiting for lunch. It was...
As if you were recommending some screen, LG screen. Can you?
Oh my goodness, yeah, I have not sent that to you, right? Why don't we look at it, LG 42 inch? Because it is in my purchase history, LG 42 inch 4K. Yes, this is the one.
Oh, okay.
And
LG is pretty good.
remember, you want a computer monitor. You never want a TV to act as a computer monitor.
Yes.
So that is important. Let me put this on the Slack. I think all students should have one. It's really very good, guys. Once you get used to big monitors, and especially in dual monitor format, it just does wonders to your productivity and concentration, because you know your entire field of view is taken over by the computer monitor. So you don't have distractions. You don't see distractions. You're completely absorbed in what you're doing.
how is this different from a TV?
See, the way, if I remember, obviously I'm not an expert, but the way they do it is completely different. These are designed for static images. TV is designed for dynamic, you know, moving images. Computer monitors have round pixels, high resolution picture, very sharp pixels. A TV, on the other hand, has square pixels. The other thing is, it is called 4:4:4. There's a technical term, means the signal that the computer sends is 100% projected onto the screen. In a TV, you don't do that. The TVs are cheap, you know, they're commodity items. So you achieve that by undersampling. There is a lot of undersampling happening. That is why those are called 4:4 1:1 or 4:2:1. They all undersample. And because they need to show you motion quickly and with a cheap processor, because the TV is a commodity item, people are very price sensitive. So that is one. And the other is the color gamut. A good monitor will give you a sRGB color gamut close to 100%, even more. Whereas a TV will give you a color gamut that essentially sucks. So that's why you pay more for a computer monitor than for a TV. Some people are fine with TV also. I mean, it's not that TV is too bad. 4K TVs are pretty good. If you don't have the budget to buy a TV, see, here's the thing. A computer monitor is $700. $700 can buy you a giant TV, isn't it? Here it buys you a rather tiny monitor, 43-inch monitor. 43 is pretty good, big for computers, but small for TV.
You don't get all the connections either. You don't get HDMI.
Oh, that's right. You don't get ports, HDMI, USB-C. So these are just more sophisticated beasts. There's no compromise in these things.
2.2 is pretty useful.
They're really.
Thank you, Asif. Thank you very much.
Yeah. Nice, Shankar. Get a few and then let me know how you feel.
Okay.
Bye, guys. I'm stopping now.